Okay, guys, so today we will be learning about angular velocity and its relation with the linear velocity. So, before we do that, let's try to understand what's the meaning of angular velocity. Before we understand the angular velocity itself, we must understand what is angular displacement. When in a circular motion, particles are moving in a circle around a common axis of rotation. As you can see in this case here, that the body is revolving around this axis in a circular manner. However, in a particular time, in a given time, the angle covered by the particle is called as the angular displacement. This here, the one which I am highlighting, is the linear velocity, linear displacement of that particle at that time. But this angle is the delta theta, in this case, is actually the angular displacement. And angular velocity, which we denote by omega, here is actually the ratio of angular displacement for that instant of time, for, let's say, angular displacement divided by, it's the ratio of displacement to the time interval, for which the body displaces, during which displacement occurs. Now, let's take this as a rigid body. This is a rigid body, the one I highlighted in the green color. This is the rigid body, and in this rigid body, it is rotating about an axis, a given axis. In this, the z axis is the one around which the rigid body is rotating. So then each particle of the body moves in a circle. Every single particle of the body is moving in a circle. This circle lies in the plane. Let's say this is a plane here. We are taking just a plane of the rigid body, a slice of the rigid body. So the plane here is perpendicular to the axis of rotation. This is the axis of rotation, and this plane is perpendicular to it. They are 90 degree. Now, consider a rigid body rotating about an axis passing through O and perpendicular to the plane of the body, as shown here. Each particle of the body moves in a circle having center on its axis of rotation. Every particle which is moving and rotating is actually around this axis of rotation. Let's consider one of the particles which is at an instant is at the position P. So let after time delta t, so I'm writing time interval as delta t. Right now it is at the position P here. So time delta t, after time delta t, the average angular velocity of the rotating body. We are now going to figure out the average angular velocity. Omega will be equal to ratio, right? Angular displacement, that is delta theta. This is the angular displacement, small, and the time for it was delta t, for time period delta t. Now let's say we want, this is kind of the average angular velocity that we have figured out. Let's say now we have to find out the instantaneous angular velocity for a particular instant, like time t. At time t, what velocity can be? So instantaneous angular velocity, omega, let's say the average was omega bar, and omega itself, instantaneous angular velocity of the particle, is, we have to limit it. instantaneous means when there is no time period. It's simply delta t approaches 0. Delta t approaches 0. That there is no t2 minus t1 will be approaching 0 for a particular instant of time. So we'll write it as a limit. We have to take the limit delta t approaches 0 for omega average. This will be limit delta t approaching 0 delta theta by delta t. Now when you take the limit of delta theta by delta t, it is actually d theta by dt. This is the instantaneous angular velocity, d theta by dt. Now it's an axial vector. It's a vector. Angular velocity is a vector, but it's an axial vector. In other words, it follows the right hand thumb rule in order to find its own direction. So this vector here, omega, angular velocity vector, its direction can be found using the right hand thumb rule, where the fingers are showing the direction in which the particle is moving, and the direction of your right hand thumb accordingly will show you the direction of the vector itself. So this is an axial vector, so it will be along the axis of rotation. It will be, if the particle is moving like this, and these are the direction of your fingers, right hand fingers, and the thumb will be upward. So this thumbs up will be the direction of the vector, and it will be, now we are talking about the angular displacement by time. So the SI units of angular velocity will be radian per second. It will be radian per second, and it is dimensionless. So m0 l0 t is minus 1. Okay, angular velocity, yes, t minus 1, m0 l0 t minus 1. It is not dimensionless, but this is the dimensional formula for that. There's no units for radian. We can say there's no formula for radian, but we have per second, so t minus 1. Now it can be positive or negative. Let's understand this, that angular velocity can be positive or negative depending on the direction in which the body is rotating. It's very important. See, so in this case, as we are saying, the body was rotating anti-clockwise, right? It was anti-clockwise like this, so direction was up. In this case, omega will be positive. For anti-clockwise direction, the body is rotating in the direction of increasing theta. As you can see here, the angular displacement was increasing in this direction. We'll be going from there, point P to point P dash. The theta was increasing, so it will be, omega will be taken positive in that case. But let's say it was in the position P dash and then coming back. It was decreasing now, let's say. That means the particle is now moving clockwise direction. Then the direction of omega will be downward, and omega itself, we have to take it as negative. It will be negative. Omega will be negative for anti-clockwise. Sorry, clockwise. For clockwise direction of the body, omega will be negative. Okay. Now let's talk about the vector relation between linear velocity and the angular velocity. It is simply v is equal to omega into r. Linear velocity v is equal to omega times r. Okay.